The name of this video is Toroidal Solenoid L, self-inductance. For simplicity of calculation, let us consider a toroidal solenoid which has a rectangular core with a single wire, filiform wire around it. In other words, the way this works is that this is our revolution axis gamma z, and first let me sketch only half of it for simplicity, then I will briefly sketch down here what it looks like overall. So let's do this. So this is our gamma z axis, which eventually also coincides with the z axis of a cylindrical coordinate system, characterized by an r axis, which let's say is this here. This is the origin of this system. Oh, and the rectangular cross section with the single, with the filiform wire around it, it looks like something like this. This is one loop, one of the capital N loops. Okay, I remind you that, so let's write down here the dimensions of this loop. So since this is R, this distance from O to this point here, we call it capital R1, which is clearly smaller than capital R2, which is here. These are these 2 points, whereas this point here and this point here, this is Z naught, a constant, and this is Z naught plus H, the height of this loop. The loop is characterized by an orientation, which, as always, we orient it in this way. So the current goes down, let's do it in yellow. The current goes down like this. This is I, and the orientation of the loop is also this. This is gamma L, where L is for a loop. This is one of N loops. One of capital N loops. Okay, so given this orientation of gamma L, the normal unit vector for this surface on the board, of course, will be this. So it goes inward. So that is N associated with L is equal to U bar phi, because bar phi, of course, goes in this direction, in this cylindrical coordinate system. Similarly, if the current goes like this, we know that the magnetostatic field generated by this current will be also pointing in this direction. This is B, due to the current I. Inward, of course. The same direction as N. The right-hand rule, it goes in. So B goes in, N, L, which is the same as U bar phi, they go in. This area, which has gamma L as a border, we call it capital sigma L, and is an open surface across which we want to calculate the flux of the magnetostatic field B. Okay, so just to simplify, to show in brief here what it will look like in general. So this is a symmetric construction, of course, so it will look like something like this. So we have the cross section here, and then opposite with respect to this point here, there is a similar cross section on the other side, like this. And so, and the toroid, of course, go all the way around. And similarly below, which I'm not going to sketch for simplicity, but that's what you need to remember, that this is only this cross-sectional area here is this cross-sectional area. So I'm not sketching the other side of this construction, which is of course symmetric with respect to gamma z for simplicity. Okay, so now that we know that, and let's remind ourselves, of course, that the current goes in this direction. Here, this is our current I. Here, of course, it goes in this direction. This is our current I, which is obviously the same as this one up here. All right, and we have all the same conditions. We have capital N loops. They are, many of them, equally spaced, so one per meridian semiplane, in this case the ORZ plane is in meridian semiplane stemming from gamma z. Okay, with all these conditions in mind, we want to compute effectively the inductance L of this object. To find inductance, we always want to compute the flux associated with the field B due to this current I. So we calculated already B from before. So we know that B, with respect to exactly this cylindrical coordinate system, is mu naught Ni divided by 2 pi r times u phi, which is the unit vector in the var phi direction, the tangent unit vector in this direction. Okay, that's what we get for B. So if this is our B, the flux through the open surface capital sigma L, this surface here, of this B dot n dA, what n and L dA, but NL is nothing but u bar phi. So now we can start to use this expression here. We plug it in. U bar phi dot u bar phi is 1 because NL is u bar phi. And so B, all the constants, we can take them outside the sign of integral. So we get mu naught, which is a constant, n, which is a constant, I, which is a constant, divided by 2 pi. This is a double integral, so we need to integrate along z from z naught to z naught plus h in dz. So the area dA is dz times dr. There's nothing else, it's just dz times dr, okay? dz times dr, this is dA. Okay, and so here we have the integral between capital R1, which is more than capital R2, of dr over r. That's the only thing left. These are all constants. Dr over r, we have it. You find already take care of this with this. dz, we took care of it. And so the final result here is nothing but h. So we get mu naught, capital N, I, h. Z naught plus h minus z naught is obviously h, divided by 2 pi. And eventually we are left over with this integral, which is the natural logarithm of R2 minus the natural logarithm of R1, so it's the ratio of R2 and R1, which is clearly a quantity larger than 0, because R2 is larger than R1, as we can see from here, and this is a logarithm, which is monotonic increasing. All right, so then the next thing we want to do, we want to find, so this is the flux associated with just one loop. And so what is the flux associated to all loops? Well, is n times the flux associated with one loop. And so it's n squared here. So we get mu naught n square I h divided by 2 pi and natural logarithm of R2 divided by R1. Now, in order to find finally the inductance, we know that the inductance is phi over I. And so we plug in this expression here and get rid of this I, and we get that the inductance is nothing but mu naught times n quantity squared times h divided by 2 pi natural logarithm of R2 divided by R1. And this is the final expression we wanted to get for the self-inductance of a toroidal solenoid. Important to note, there is this n square, so the self-inductance scales with n squared. The more loops you put, the better, the bigger it gets with n squared. Okay? So to recap this video, we wanted to find the self-inductance of a toroidal solenoid. But to simplify it, we consider a toroidal solenoid with a rectangular cross-section with just one wire like this, which goes around the gamma z axis, with this cylindrical coordinate system where the dimensions are R1, R2, and h is the height of this rectangle. We orient it suitably as we have done here. We calculate the flux, the field, we already know the field of a toroidal solenoid. And so this is the flux in this cylindrical coordinate system, which is positive. This is for one loop. Then we have many loops, so we multiply times n, equally everywhere, because it's all equally homogeneously organized. And so we get this famous n squared logarithmic dependence, and clearly this quantity is always a positive quantity as expected for a self-inductance, because R2 is larger than R1. This is n squared, and all the rest is positive quantities. That's it.